Hello, welcome back. In this segment, I will introduce you to the notion of natural deduction. In logic, we have collection of proof rules. The proof rules have multiple benefits. For example, you have a bunch of premises and you would like to draw a conclusion. You need to apply well-defined proof rule. So you have the proof rules. You need to somehow use the proof rules to arrive at the conclusion from the given set of premises. You have, say, n premises here. I call it phi 1, phi 2, phi n premises. You imagine each premise is just some logic formula we talked about, like P and not Q implies R is one formula, not R is another formula, P can be another formula. So the n formulas like that, set of premises. And the conclusion is what you can derive by applying the proof rules. Okay. So proof rules are for conjunction, for disjunction, for implies, for not. Those are the four major logical connectives, and we have proof rules for them. How to use them to deduce new things, essentially. That is the part of the natural deduction. Okay. To give you a concrete example, suppose you have P and not Q implies R, not R and P, therefore you can conclude Q. We can reason about it ourselves and somehow convince that this is true, but that's not how mathematics or computer science works. You need to have formal proof of your argument. Okay, on what basis would you be able to combine these premises? Which set of proof rules can you apply to arrive at Q? That's the whole study of natural deduction. And today I will start with the very first proof rule related to conjunction. So I'm not going to prove this today. This is not part of the proof. Okay, I'll start with the rules of conjunction first. There are only two rules actually. Suppose you have, say, two symbols pi and psi, and you have somehow proved that pi and psi are true. What it means is that you can argue phi and psi will also be true. Okay, this is rule number one. This is called, on the side, you would say, and introduction. You're introducing an and. You have established proof for phi and psi separately. You can use and introduction to come up with a new statement, phi and psi. That's the first rule of conjunction. The second rule is the opposite, meaning suppose you have already established the truth for phi and psi, you can argue that phi must be true. This is called eliminating an and. You can also do the same with psi. Phi and psi, you can also eliminate just the psi because you already established this is the phi and psi is true. Okay, what is this rule called? This rule is called and elimination, one of the components from the upper formula. So this is something that you already established. This is like a premise. Phi and psi is a premise. You can conclude phi and psi. Here, phi and psi is a premise. You can conclude phi. Similarly, psi. So these two rules are going to help us whenever we deal with conjunction, right? We can appeal to them. This is called the and introduction. Yeah, you're introducing I stands for introduction. This is called and elimination. Okay. And these two rules are called rules of conjunction. So I will use the rules now to show you how to prove some very basic properties. Let's talk about proving, for example, associative property. Okay, we will directly apply rules of conjunction to prove that and is associative. I'll actually use a computer to type in the proof and it will check our proof is correct. P, let's say P is some proposition, Q is another proposition, R is another proposition. I wanted to prove that P, Q, and R, yeah, is same as P and Q and R. Actually, you can also do other way around. I will use only these two rules to prove that these two things are equal. Okay, or you can deduce one from another. Let us prove that P and Q and R is same as P and Q and R. We will follow the proof rules one by one to construct the proof. So this is our hypothesis. P and Q and R with the bracket for P and Q is the hypothesis. We need to arrive at this conclusion. Okay. All I have to do is apply the proof rules that we just introduced. So I'll start here. Having known that an understatement is true, I can use the and elimination to extract the first component. Okay, the first component is P and Q. This is because I'm able to eliminate one term from the understatement. Okay, I'm eliminating one term from the understatement. This one means the line number one. Okay, you're applying and elimination on the line number one. And now I'll add one more. I will eliminate one more term now from the second line because I can do that using the and elimination on the second line. I can also do the same for Q, right? I can get Q from the second line again. From the first line, I can also eliminate R because it's an AND. Okay. So eliminate means we know that R must also be true, given that P, Q, and R is true. That's the hypothesis, right? This is the premise is true, obviously. So I'm going to now eliminate from the first line. And now I need to combine Q and R from fourth line and the fifth line, which I can do because we can apply one of the rules we just learned. That is introduction rule. We are going to introduce combining lines 4 and 5. Okay. So we are saying and 4, 5. So we got that done. Then we can also, since P is true, Q and R is true, we can combine them together using the and. Okay, line numbers we need to combine are 3 and 6. All right, so we arrived at the conclusion. This is exactly what we need, and we can ask the proof checker to check whether our proof is correct. Yeah, we got a congratulations message. Our proof is correct. All right. So what have we done so far? We just systematically followed the rules of conjunction. Either we eliminated some components or we inserted the AND by knowing the individual components are true. Okay, this is basically how you can use rules of conjunction to prove statements involving conjunction. Okay, what did we prove? We proved that P and Q and R is same as P and Q and R. Okay. In this case, I have derived the proof manually and just used the proof checker to check the correctness of the proof. But there are a little bit more advanced ones where we can ask the computer to help us to come up with a proof. Later, you will see I will prove these kinds of things using SAT solvers. SAT means satisfiability solver, but I want to give you an impression that all of these advanced solvers are based on a collection of rules. The one that we just started today is rules for conjunction. Okay, let's make one mistake and see whether the system is catching us. Let's say instead of P and Q coming from line number 2, let's say Q coming from line number 2, I will put line number 1 instead. It should not be possible for me directly to take Q from line number 1, right? I have to go through line number 2 and then only I can come to line number 4. I can't skip something in between. That's not correct, logically speaking. Let's see. You see, sorry, there were errors. It is not a proper application of the rule for lines that I have given. Okay. So line number is not correct. That's what it's saying. So you have to go and fix it. You can't get Q just from line number 1. You can only get it from line number 2. Okay, because P and Q is one component. You can apply elimination. Why can't we apply? Because, you know, you got to think like this. P and Q, think about it as like one component. Okay. So both P and Q are hidden there. We can't pull P and Q alone from that thing. So you have to pull P and Q together, and then you can pull P, Q separately. All right. So we can now check the proof and complete it. Yeah, this is correct. Okay, that's basically the idea of natural deduction. Thank you very much. That's all.